right, welcome to session 1.5. The title of session 1.5 is inverse functions. So in this session, we're going to take a little in-depth look at inverse functions. But remember, again, this is a review. So we will be moving kind of quickly. Our objectives are to verify that one function is the inverse of another function, to know how to do that, to be able to determine whether a function will or will not have an inverse function, and then to take a look at how those 6 trigonometric functions got their inverse functions. Now, unfortunately, this is going to be a little bit of a repeat because we did take a look at this in section 1.4. On the trig section, we took a look at that there. We'll just take a look at it again, but we'll go kind of quickly through there. All right, so first off, let's just go ahead and take a look at a simple example. And by simple, I don't mean easy. Simple is a word that we use in mathematics to mean uncomplicated. So we're going to take a look at an uncomplicated problem. Okay, so suppose that you have the function f of x, and f of x is defined to be the function x plus 3 from the set A, 1, 2, 3, 4, to the set B, 4, 5, 6, 7. It could be rewritten, differently written, as the function f defined to be a set of ordered pairs, where every ordered pair represents both an input, a value from the first set A, and an output, a value from the second set. Remember that one way, an alternate way to represent a function is to define it as a set of ordered pairs, where each of those elements of that ordered pair represent a domain value and its corresponding range value, or if you prefer, an input value and an output value, or if you prefer, and x and y, although x and y are kind of like the least specific way to describe it because there's nothing in mathematics that requires that inputs be x's and output be y's. It's just a fairly standard way of saying it. Okay. All right. But if we interchange the first and second coordinates, that is if we take the domain value and switch it for the range and the range for the domain, we can come up with an inverse function. Okay. And we use this notation right here. Now, a little bit of notation issues. There are a limited number of things, symbols, and a little bit number of places, locations, that we can put symbols. So we reuse symbols in mathematics. For example, if I asked you this, what does that mean? You would say, oh, well, that's a negative 1 in the exponent position, so that means to take the reciprocal, 1/3. But if I ask you this, you say, well, that's a negative 1 in the exponent position, but that does not mean 1 over f. That means the inverse of f. Okay. So how do I know when it means to take the reciprocal and when it means to take the inverse? Well, it's not just the notation and where the notation is, but it's like, what is the notation attached to? If the notation is attached to a variable, that means to take the reciprocal. If the notation is attached to a constant, that means to take the reciprocal. But if the notation is attached to a function, that means to take the inverse. And we just know that because we've been trained and taught it. But just be careful with that because it is kind of easy. What if I did want, though, that? Well, what I'd have to do is I'd have to wrap it up in a set of parentheses and then put that negative 1 on it as a way to say, hey, look, this isn't an inverse notation now. This is take the reciprocal notation. All right, so just a notation statement. Right. Now, when you do find the inverse, it switches the order. So if f went from A to B, then f inverse would go from B to A. Now, the idea here with inverses is one undoes the other. It's probably easiest to take a look at it in this sense. Just make a picture. I've got a set A up there up top, and there is my set A. I've got a set B down here on the bottom. There is my set B. And if F takes things from A and delivers them to B, its inverse would take things from B and deliver them back up to A. If f takes little a and drops it off down here on little b, then inverse should pick up b and take it back to a. And in a perfect world, every function would have an inverse like that, and we could just do something and then undo it and do something and undo it. You may have noticed that about mathematics. We like to do things, and then we like to undo those same things. Okay? We give you equations and say, okay, here's a value for y, solve for x. Here's a value for y, solve for x. Here's a value for y, solve for x. And then once we get that figured out, once we know that you know how to do that, we change the rules on you. And then we say, okay, well, here's a value of y. Can you take that y and turn it back into an x? Which is essentially kind of the inverse there. We're doing and undoing, we're doing and undoing. So then we can undo and do and undo and do and undo and do. Okay? The mathematical definition of an inverse function says that a function g is the inverse function of the function f when the composition f of g is equal to x for each x in the domain of g, and the composition g of f is equal to x for each x in the domain of f. The function g is then denoted by f raised to the negative 1, or read f inverse. So what are we looking at here? We're looking at a definition. And what does it say? It says that if you do this, you should get back to x for any x that is in the domain of the g. Now remember, the g is the inside function here. But there's an and here. So this must be true, as well as this must be true. And this says do the functions in the other order, so that x is in the domain of f. All right, so here's some important information about inverse functions. If g is the inverse of f, then f is the inverse of g. Those are logically equivalent statements. Okay. Another thing that is important to know is the domain of the inverse is the range of the function. The range of the inverse is the domain of the function. Okay. And the third thing about inverse functions is every function doesn't have an inverse. A function need not have an inverse function. But if it does, then that inverse function is unique, meaning there isn't another one out there somewhere. This is it and the only one. Okay. All right, so our job here is to show that the two functions are inverse functions of each other. Well, the definition says these two things will be inverse functions if these two compositions ultimately end up back at the statement x. That is, if f of g of x is equal to x and g of f of x is equal to x. So I'm going to go ahead and work through this. We'll work through the one on the left first. Okay. We're going to perform f composed with g of x for these two functions right here. Okay. So that is f of g of x. First step is just to replace g of x with what the function g of x is defined to be. It is defined to be a big cube root, and under that cube root is the fraction with numerator x plus 5 and denominator 4. Okay. Now we need to apply the f function to this. Okay. The f function says take whatever's in the parentheses, cube it times 4 minus 5. So that's going to give me 4 times the quantity, the cube root of x plus 5 over 4 cubed minus 5. So do you see the blue there as being the f function and the orange there as being the g function? All right, so I'm going to take the blue and the orange and put them all together. Now, inside those parentheses, I have a cube root, and when you cube that cube root, we get 4 times the quantity x plus 5 divided by 4 minus 5. That's going to get, well, the 4's are going to cancel, so that's going to give me the statement x plus 5 minus 5, which is x. Now, my job was to show that f of g and g of f both equal x. So I'm just going to start there. I've got f of g is equal to x. I'm feeling good. I'm halfway done. Now I'm going to do the other one. Right? G of f. Right? So I'm going to perform the composition g composed with f of x. So that's g of f of x. I'll start out by doing the same thing I did before. Replace the inside function with its value. In this case, f of x was 4x cubed minus 5, right? And now I'm going to apply the g function. Now remember, the g function says take whatever's in the parentheses, add 5, put it in the numerator, divide it by 4, then wrap it up with a root. So when I do the g, I'm going to have the cube root of 4x cubed minus 5 plus 5 divided by 4. Do you see how the black represents g, whilst the red is representing the x, or in this case the f of x? And now if I start cleaning that up inside the parentheses there, do you see how the 5's will cancel? And so that's going to give me the cube root of 4x cubed over 4. 4's are going to cancel, so that gives me the cube root of x cubed. And the cube root of x cubed is x, because it's an odd root. Okay? Just as a complete note, remember that the square root of x squared is not equal to x, right? The square root of x squared is equal to the absolute value of x, because it's an even root. This is an odd root. We don't have that issue here. Okay? If you're confused by that, you should research it. Take a look at that. Now, if you were to have graphed these two functions, here's the graph that you would see. Okay? This one down here is the function f of x. This one over here is the function g of x. And this really cool thing that happens when you graph inverse functions and the function and the inverse function on the same set of axes. By the way, the dashed line is the line y equals x. Is you get these beautiful, cool reflections across that line y equals x. And that's like a visual way. Now, visually is cool, aesthetically it's nice to look at, but it would be very, very hard to see an inverse function graphically. One of the challenges you have with this to see that reflection is you have to make sure that the window is properly sized so that the aspect ratio is such that you can see a reflection nicely. Your calculator is terrible at this because the window on your calculator is wider than it is tall. The physical display is wider than it is tall. And unfortunately, when it graphs things, it doesn't graph them with an aspect ratio that makes you actually see what you should see. If you ever try to graph a circle on your calculator, you know what I'm talking about. It looks like it's stretched out sideways because the width is physically wider than the height. And so the graph gets distorted. And so this, while this is beautiful to look at, I mean, it's gorgeous. I mean, look at that thing. The gorgeous reflection I'm seeing there. I'm so happy looking at this. But it's hard to make sure that every time you graph something, it will truly represent the way it should. So be careful with trying to use this as a tool to determine whether two things are inverses or not. Hey, speaking of whether two things are inverses or not, does every function have an inverse function? Well, the short answer is no. The longer answer is no, and here's how we determine whether something does or does not. Now, the quick and dirty way to do it is use something called the horizontal line test. And the horizontal line test is what we use to determine whether a function does or does not have an inverse. But more importantly, why does it work? Okay? So the test states that if a function has an inverse, then every horizontal line will only ever touch it at most once. So see how this one has two intersections? Okay, that's an issue. Why is that an issue? Well, if I go back to my drawing from earlier, remember the A and the B, and the idea that you could have an inverse if little a got sent to B, and that was, wait, it was like this, right? This was the F. And then the inverse would take B back to, the inverse would take B back to A. Right? Here's my problem. What if there's another value over here, and we call it C? But C also goes to B under that F. I got two places that start, two values that take me to the same domain value, two range values. So if I'm at B and someone says go home, I don't know where home is. Did I come from A or did I come from C? And if I don't know how to get back, then I can't really be an inverse. Okay? And that's what this picture over here is trying to show. Here's two domain values that both have the same range value. And if you have two domains with the same range, then there's no way to get back. Right? So a function has an inverse if and only if it is 1-to-1. And 1-to-1 means 1x gives you 1y, and 1y gives you 1x. All right, so let's look at this example right here. Which of the functions have an inverse function? So which one of these will have an inverse function? Well, let's take a look at this one first. Given what I know about it, I know that that is a cubic equation that has been vertically translated one unit down. So it's going to look something like this if I graph it. And so if I were to attempt the horizontal line test, pretty sure that's never going to have an issue. And if that never has an issue, I think that I've got a winner here. I think that I've got a function that would have an inverse. Okay? And so I would say that one does. Now let's look at this guy. Wow, it's a cubic equation, but this term right here makes me think that maybe it wiggles in the middle. And if it wiggles in the middle, something like that, then it's going to fail that horizontal line test. Now, I'm not sure what exactly that graph looks like. It's more complicated, but I know how to find out what that graph looks like. I can come over here to Desmos and say y equals x cubed. Caps lock was on for some reason. X cubed minus x minus 1, was it? Or was it plus 1? I think it was plus 1. Yeah, plus 1. And if I take a look at that graph, do you see that wiggle right there? And what does that wiggle tell me? I'm pretty sure that horizontal line test is not going to work. And if that horizontal line test fails, then what we have here is we have a function that does not have an inverse. So it does wiggle. It doesn't wiggle across the x-axis like I sketched it there, but because it wiggles, no, and yes. And using the graph is an appropriate way to support my answer here. I don't need to go any further. I can just show it that way. Okay? Now, what if your job was to find an inverse? Well, we're at about 18 minutes right here, so I'm going to stop this video and come back, and the second part of section 1.5 will be how to find that inverse.